Joey and Chloe and their daughter Zoe all have the same birthday. Joey is 1 year older than Chloe, and Zoe is exactly 1 year old today. Today is the first of the 9 birthdays on which Chloe's age will be an integral multiple of Zoe's age. What will be the sum of the 2 digits of Joey's age the next time his age is a multiple of Zoe's age? Okay. So first, I'm going to kind of outline some stuff that we know immediately upon reading that. Let's let Joey's age be J. I know Joey's age is 1 more than Chloe's age, so that equation is going to work for that. And I know Zoe is 1 year old, so that's going to be her age. And the way I'm going to approach this problem is I'm going to first try to figure out what Chloe and Joey's age actually is, and then we'll work from there. So one equation I can set up, so let's say A and K are integers. Writing this equation where there are 9 times Zoe's age is going to be an integral multiple of Chloe's age. If I write C plus K equals A times 1 plus K, this is an equation for that scenario. Basically, adding some number to Chloe's age, there are going to be 9 times where you plug in a value for K, and that's a solution of this equation here. So basically, there are 9 solutions for K. And A is basically saying how many times bigger is Zoe's age from Chloe's. And again, the 1 is there because Zoe's age at the very beginning is 1. So that's a little explanation on that. So some manipulation I'm going to do to this equation. So I know C plus K, I can rewrite that as C minus 1 plus 1 plus K. And that actually equals A times 1 plus K. Okay. And so subtracting 1 plus K from both sides, I'm going to rearrange and I can get the equation C minus 1 equals, it's going to be 1 plus K times A minus 1. So basically, I just rearrange the equation. It still holds that there are 9 solutions for K. And that implies that there are also 9 solutions for C minus 1. And that implies that C minus 1 is divisible by 9 different numbers, 9 different integers. Okay. So now I want to start thinking, what could C minus 1 be? And to try to figure that out, I want to think about what the prime factorization of C minus 1 could be. So what are some prime factorizations that are divisible by 9 different integers? So the C minus 1 prime factorization could be some integer a to the 8th. And notice that's divisible by a to the 0, a to the 1, dot, 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 all the way a to the 8th. There are 9 solutions there. So that's one possibility. Another one could be, do this, same thing. Another prime factorization could be a squared, b squared. And that is divisible, I'm just going to do quote marks there. That is divisible by, it's going to be a squared, obviously 1, ab, a squared b, ab squared, a squared, b squared. So we've got, and then also b and b squared. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 there. Those are the only prime factorizations that are going to work. But I'd imagine if you're trying to solve this problem, you would try others. Just know that you'd also try a b to the third. As that, you'd find that that's divisible by 8. It has 8 different factors. You might try a b to the fourth. That's divisible by 10 different factors. You may also try ABC. That's divisible by 8 different factors. And then seeing that none of those are 9, you can see that definitely ABCD wouldn't work because that would go over 9. A b to the fifth wouldn't work. That would go over 10. These are the 2 prime factorizations that are going to work. That a to the 8th prime factorization, let's say even a is the smallest prime number. So let's just say if the prime factorization were a to the 8th, even if a were 2, the smallest prime number, 2 to the 8th that's 256. That's a pretty big number. I highly doubt that Chloe is 256 years old. So the prime factorization that we're going to go with has got to be a squared b squared. So we now know that c minus 1 is equal to a squared b squared. Notice that a squared b squared can be written as ab squared. That means it's a perfect square. That's interesting because now I'm going to try different numbers to see what's going to work. So thinking about all the perfect squares here and a reasonable age for Chloe to be, so as small as possible I think would be, what if, here's some testing, what if c minus 1 equaled 16? So basically it's got to be the case that that basically means 16 equals AB squared. So that just implies that AB has to equal 4. Are there 2 different prime numbers that are going to equal 4? 2 different? No. Next one we're going to try out is 25. So 25 equals AB squared. So basically AB has to equal 5. Again, there aren't 2 different prime numbers that equal 5. Next, 36, AB squared. So AB equals 6 here. And you can see that, well, if A equals 2 and B equals 3, both prime numbers, that equals 6. Checks out. And you can try the other prime numbers. You're going to find that the others are 49, 64, 81. All of those aren't going to work. So basically, I've just found that c minus 1 is equal to 36. So since c minus 1 equals 36, I know that c equals 37. And going back to the equation we had above, j equals c plus 1. So j is going to equal 37 plus 1. J equals 38. Okay. So now, moving on to the second part of the problem, I need to find out when is Joey's age next going to be an integral multiple of Chloe's age. So remember the first equation we made for the whole integral multiple stuff, if I do j plus k equals a times 1 plus k, that's the same thing we did with Chloe, but now we're doing Joey, and I don't know the number of solutions for k, but I'm going to try to figure out what k is. So rearranging the same way we did above, I know that j minus 1 is going to be equal to 1 plus k times a minus 1. And so something to note here, I'm actually going to plug, I know what j is. J is 38. So I know that, plug in 38, 37 is equal to 1 plus k times a minus 1. And you'll note that 37 is a prime number. So this value right here, a minus 1, the only values that are going to work for a are going to be a could either equal 38. In that case, k's got to be 0. That's just the initial situation where Zoe is 1 and Joey is 38. The other scenario could be a is equal to 2, right? Because 37 is going to be divisible by 37 and also 1. So what we don't want to look at is when a is equal to 2. So I'm going to plug that in. I'm going to do 37 is equal to 1 plus k times 2 minus 1. And so I get 37 is just 2 minus 1 is 1 equal to 1 plus k. So I get 36 is equal to k. So that's basically saying the next time Joey's age is an integral multiple of Zoe's age is going to be in 36 years. So in 36 years, Joey's age is going to be 38, what he is now, plus 36. So he's going to be 74 years old. So when he's 74 years old, that age is going to be an integral multiple of Zoe's age. It's going to be 2 times Zoe's age. And so I found that number, and now the problem was just asking the sum of the digits of that age. And so I can do that. It's 7 plus 4 equals 11. And that is what we wanted to find in the end. The answer is E, 11.